In AD 52, a new stream of water reaches Rome from the hills east of the city. It has traveled for tens of kilometers without a pump, an engine, or any machine forcing it forward. Most of the route is almost invisible. Only near Rome does the system rise onto the giant arcades we remember today. This is how Roman aqueducts actually worked. The basic principle was simple. Water flows downhill. Roman engineers began by finding a source high enough above the place they wanted to supply. Springs were especially useful because they could provide relatively clean, continuous flow. Some aqueducts also drew from rivers. The source was captured, and the water entered a built channel called a specus. From there, gravity did almost everything. But gravity created the hardest engineering problem. The channel had to keep descending over long distances while crossing terrain that rose and fell. If the route dropped too quickly, the water could become harder to control. If it barely descended, small surveying errors, sediment, or local changes in the channel could interfere with flow. So the real achievement was not making water move. It was controlling the gradient. Vitruvius describes surveying devices used for waterworks, including the chorobates, a long leveling instrument that could be checked with plumb lines or water. Roman surveyors used such methods to compare elevations and establish a workable route across the landscape. And that route was rarely straight. If a hill stood in the way, engineers could curve the channel around its side or tunnel through it. If the ground dropped, they could carry the conduit across a bridge or arcade. The shortest path mattered less than preserving the hydraulic line. That is why Roman aqueducts could wander across the countryside. The famous arches were only one solution to one kind of obstacle. For much of their length, many aqueducts ran at ground level or underground. The Aqua Claudia, completed under Emperor Claudius in AD 52, ran for roughly 68 kilometers toward Rome. Its monumental arcades appeared mainly in the final approach to the city. Underground construction offered several advantages. The channel was protected from weather, accidental damage, and interference. Burying much of the route also reduced the need for exposed masonry over long distances. In some places, workers could tunnel toward one another from vertical shafts, then use those openings for access. Inside, the aqueduct was not a large river. It was a controlled artificial channel. Masonry formed the sides and roof. Water-resistant mortar could line surfaces where needed. The dimensions varied from aqueduct to aqueduct, but the goal remained the same: create a durable passage with enough capacity to carry water continuously. And the water itself was not always clean. This created another problem. The Anio Novus, also completed in AD 52, took water from the Aniene River. Frontinus, the Roman official responsible for Rome's water supply later in the 1st century, complained that this water could become muddy, especially after storms. A settling basin was built near its intake. The principle was simple: slow the water enough, and heavier suspended material can sink before the flow continues. It did not solve every problem, but it shows that Roman water engineering was not only about transportation, it was also about managing water quality. Then came the valleys. This is where the aqueduct became visible. A long arcade could hold the channel at the required elevation while the land fell beneath it. The arches were not there to push water forward. They were structural supports beneath a channel that was still descending by gravity. At the Pont du Gard in southern Gaul, the aqueduct serving Nimes crossed the Gardon on a 3-tier bridge nearly 50 meters high. The structure looks enormous because the obstacle was enormous. But the water still moved for the same reason. Its destination was lower than its source. Romans also had another option for some difficult depressions. Instead of keeping an open channel high above the ground, water could descend through closed pipes and rise again on the opposite side under pressure, provided the outlet remained below the available hydraulic head. These inverted siphons demanded stronger pipe systems and were not the default solution. But surviving Roman systems show that engineers understood how to use pressure when terrain required it. By the time Frontinus took charge of Rome's water supply in AD 97, he counted 9 aqueducts converging on the capital. They did not all carry the same water, follow the same route, or enter the city at the same height. That mattered. Water could only be distributed to places that the remaining hydraulic head allowed it to reach. A high-level supply was more flexible. A low-level channel could not simply send water uphill because a neighborhood needed it. Eventually, the water reached the city. Now the problem changed. Moving water across the countryside was no longer enough. It had to be divided. Aqueduct water could enter distribution reservoirs, where branches and pipes directed portions of the supply toward different destinations. Public fountains were especially important. Baths, basins, imperial properties, and some private users could also receive water, depending on the city, period, and legal arrangements. At many public fountains, water could flow continuously. Overflow was not always wasted. It could pass onward into drains or be reused locally, helping move wastewater through parts of the urban system. In Rome, this distribution was regulated. Frontinus describes calibrated outlets and official pipe connections. He also describes fraud, oversized connections, unauthorized branches, and pipes secretly punctured to steal water. The engineering system had created an administrative system. Because gravity could deliver water continuously, someone also had to decide who received it, how much they received, and who repaired the network when something failed. And failure was constant. Mineral deposits accumulated, sediment entered channels, leaks developed, masonry decayed, pipes were damaged or altered. Vegetation and construction could threaten exposed sections. An aqueduct was not a monument that could simply be finished and forgotten. Frontinus described specialized maintenance crews responsible for reservoirs, conduits, paving, plastering, inspections, and emergency repairs. He argued that small defects had to be handled before they became major ones. That may be the most important part of the entire system. Roman aqueducts worked because the Romans did not solve one engineering problem. They solved a chain of them: find water at sufficient elevation, capture it, survey a route, preserve the gradient. Cross hills and valleys control sediment, protect the conduit, distribute the flow, repair leaks, police illegal connections. The arches were only the most visible link. And this changes what an aqueduct really was. It was not simply a stone bridge carrying water. It was a gravity-powered network stretching from distant landscapes into the daily operation of a city. A spring outside Rome could feed a channel. That channel could cross tens of kilometers of uneven ground, and the same flow could finally emerge from fountains far below its original elevation. No pump was required, but almost everything else required organization. The surviving arcades still dominate the landscape because stone is what remains visible. The harder system to see is the one that kept the water moving. Surveyors, gradients, buried channels, settling basins, distribution tanks, pipes, regulations, and repair crews. The water followed gravity. Rome had to manage everything around it.